Thank you for this big audience for being still here after this 1.5 days. It's really an honor for me to give this presentation here at this closing session. And in this presentation, I want to give you some spotlights of where we found during the last time some gaps in measurement analysis, simulations, and where we see data modeling coming up more and more. So when we talk about TVA modeling beyond the deterministic theory, I want to give you a short way or a short thought on what makes TVA so special, what makes TVA so special that we make here a 2-day symposium. And from my point of view, torsional vibration analysis plays such a crucial role in vibration analysis and vibration engineering, as it has the main pillar of a concrete and commonly agreed modeling that can be verified by measurements. We all are players in this field because we can change input data without having fear about IP protection. And there are acceptance criteria. We have clear go and no-go areas. And exactly this last one, I want to emphasize a little bit more to give the link to the non-deterministic theory. So talking about acceptance criteria, one of the first key milestones was when it was found out by August Wöhler that materials could fail under repeated cyclic loading. The stress levels were below the yield strength, but the number was high enough to fail, that these are failed. And by major contributions from other very famous guys in this field, Miner, Palmgren, Cutwell, Weibel, they developed a theory that allows us today to decide go or no go. And how do they do this? They were doing intensive testing, took the result, did statistical evaluations, and derived criteria for acceptance criteria based on this. So whenever we are doing torsional vibration analysis, and whenever we are saying something has to be good enough for being there, we are doing somehow a simplification based on statistics. And this, I wanted to go for this way. But if we stretch this out to non-deterministic behavior, I want to somehow give a definition or a hint of a definition what I mean with non-deterministic in this entire talk. And everything is called non-deterministic here, which is not clearly predictable. And it's always important to have the observer's view. If you are the observer and it appears to you random and unexplained, this is what I mean under non-deterministic. And take this picture here, and this was generated by AI, so I just tipped to ChatGPT, please give me a picture of throwing 2 dice, and you start to play with ChatGPT a little bit, and you start to gamble a little bit, and you will definitely lose some money as long as you notice that these dice are manipulated by ChatGPT. So the left one has 2 fives if you want to continue this gamble. So what do we take away from this? So first of all, never start to gamble against AI. They're not playing fair. And second, if you don't know the real source, the outcome is surprisingly, and you need to understand and to have to work a lot for this. And this is what I want to show you on different time scales now. We are starting on the shortest time scales, talking about milliseconds, and we're raising the entire time range until the lifetime of a powertrain. Of course, we go strictly in order, and we start with the shortest one. And I want to show you some results that we had on single combustion events and cycle-to-cycle comparisons during the last years. So what is the non-deterministic behavior behind combustion events? And these are these cycle-to-cycle differences. We have here a picture of a really early stage of the engine development of an ammonia engine. And we see here a clear variation in the peak pressure levels. We have here a blue line, which indicates somehow a design curve, which is an average value. So we have to somehow take all these measurements and have to make it somehow simple, accessible for the torsion vibration analysis guys. However, how to identify those deviations in real life? And I have brought with me one really interesting example. So there was on a power plant with an 18V engine, a load test for a dual fuel engine. The first time we had operation in diesel mode, and then they switched to gas mode. And I think if you compare the two pictures on the left-hand side, we have a really stable signal, just small fluctuation. And as soon as we are switching to gas mode, we see huge fluctuation appearing. So the question is how to deal with it. Yesterday we had a very interesting talk who was asking if this is a storm in the teacup. I want to give another hint. So if we work with statistics, what we see here, and we compare two load levels, one for diesel and one for gas mode, we typically only see the above picture. And this is what we represent as measurement analysis result typically. So mean values comparison, and we compare this what the torsion vibration analysis said. But we sometimes neglect the below picture. So we see here the variance of the different harmonic orders, and they are many orders of magnitudes higher in gas mode as under diesel mode. And if you're not taking this to account in your considerations, this might be at first sight a storm in a teacup, but in other places where you have to do a fatigue model or a damage model, it might be surprising to you that something might be failed in future. Talking about such short time events, I want to come to engine starts. We did extensive measurements on engine starts, and the non-deterministic behavior there comes from this very sensitiveness against boundary conditions. So starting from crank angle configurations, starting from ambient temperatures of the engine, starting of ignition timing versus all those participants, and all in all, it seems every start and stop the event is different. I have here two examples. And this example comes from a power generation set where engine is coupled via flexible coupling with a huge generator. And during the engine start event, we are having an engine versus generator resonance peak that needs to be passed anyway when you want to go to your idle speed. And we see here two starts, one in blue, one in red. One having high amplitudes, one having low amplitudes, both having the same acceleration rates. So the question is how to deal with this in simulations. So we do transient TVAs, assuming idealistic conditions. We assume that we exactly know what the combustion process starts and where it goes, and we end up with somehow a representation. However, if I show you now over 100 different starts, and we want to evaluate the peak loads of these resonances, we now see here a picture. Every start is different. And if you're only considering the average level, you might not catch the full picture, as peak levels might be much higher or much lower. And in this perspective, if you collect all them and you do this in a nonlinear damage model, your results might become inaccurate or not correctly either too dangerous or say on the safe side. If we expand our journey now to hours and days, we talk about weather. Weather is a good small talk theme and also a good topic for ending such a symposium like today. And I have to admit here, environmental conditions are not entirely predictable, so we have this error, we have equations behind this where small measurement errors implies chaotic behavior at some pace. So it's not purely stochastic, but it's not deterministic in the way that we commonly agree about it. So incorporating such conditions, such as here, the different waves, we have to deal with a lot on the huge time range. We have short time events, we have long-term events, and we have to somehow find a simplification, which is typically done in marine applications to adjust the engine power curve. That to say, when you have heavy water, heavy sea, you can have a heavy engine power curve that you compensate the entire effects. Let's take this from the other side. So if weather influence torsion vibrations, why not using torsion vibrations to say what the weather condition was? And this is what we exactly did. So we were starting to train a model just based on torsional vibration damper from the monitoring system of a torsion vibration damper. We had a third-party platform that provided us all the information that we needed, wind speed, direction, GPS data of the vessel. And then we just started to train the model. And in the end, we came up with a very interesting results. So thinking about an engine room device, predicting engine speed and engine direction, speed and wind direction, and we came up with a very interesting result that there's a strong correlation between these two. And we have here a picture where we have on the x-axis the real data, and the y-axis is the data what we predicted based on measurement, on the torsional vibration measurements. If it would be on the red line, it would be perfect. However, we were surprised that you can even do this on this kind of level. We did this also for fuel consumption and shaft torque, which is more naturally compatible with torsional vibration, which resulted in much better results here. But I wanted to show this other consideration by this modeling. Talking about exceeding the deterministic theory, I want to bring up data modeling, of course. We have seen here one model, and I want to take the same vessel's shaft torque model and consider how it evolves after time. And for this, we have a container vessel, and we looked on what kind of changes might affect such a data model that the prediction quality falls and falls and falls. And there are two possibilities. First are sudden changes, and others are long-term changes, such as wear and fouling. So when we look in the picture here, we have the first passage here with number 1, which is a journey through the Indian Ocean quite after the testing phase. So the prediction error is really low. We can predict based on vibration data shaft torque very well. After 4 months later, we had a similar route, but now there was an additional maneuvering. This was not contained in the test data. So we had to identify some deviations appearing, some larger prediction errors. And then something completely unexpected happened. This vessel was always operating between East China and Rotterdam, for instance. And now they changed the route. And with the change of this route, this was somehow a sudden change. Also, the quality of the prediction went down and down and down. So we could not achieve the same operation. For us, this was not expected, so it was not deterministic. For the ship owner, of course, this was expected. He has planned this long before, and therefore the observer's view is again important. And finally, after 22 months, the model was checked again, and we can see here that in the areas where we had the training data, we had a good prediction error. However, the final route was towards South Africa, where the prediction error increased noticeably, meaning such models are not always valid. They have to be retrained based on the data that you have available on a constant way. Talking about another aspect, I want to talk about maintenance and how they can affect torsional vibration analysis. I call them a disruptive event, here in the positive way, of course. And here is an example where we had on the same power plant a long-term measurement. We had the first time series where there was an initial condition, then there was a maintenance event happening here below on the time scale with the red line, and on the blue side after the maintenance. And what we identified in this way was the twist profile, as it's shown upwards and also on the left-hand side downwards, changed completely. And think about if you're doing a torsional vibration analysis before an event and after an event, and you see something like this. You won't be able to really deduce the correct stage, or you make misleading recommendations. So we see here a stable twist profile of the TVD damper, and afterwards large variation. And therefore, it's always important to have the knowledge of something like a maintenance activity or other changes on the system, might be also a retrofit solution, in order to avoid such spotlights that leaves you unclear about the correct condition. And of course, torsional vibration is strongly correlated with power, so you also have to know about the power output, otherwise you're blind towards the real deal that you have to do. And this is where I think torsional vibration analysis comes nowadays on its boundaries. So we have here limitations to really correctly deduce from spotlight measurements the correct behavior for such applications. And from my perspective, this can only be done by historic data collection, data modeling, and as data is arising, machine learning and artificial intelligence. So, what we heard today, torsion vibration behavior is influenced by variability across many timescales. We found 5 case studies that I wanted to highlight to you, which I leave as a question to you, how to incorporate them in simulations, measurement analysis, or in data modeling. And somehow you reach at a certain point the boundaries of torsion vibration analysis. And from our perspective, capturing these dynamic behaviors by using data modeling and advanced data techniques might be one way to go. And I would be happy if in 3 years we will talk again about this topic in more detail. Thank you.
Thank you, Mr. Thalhammer.